For this lesson, we're going to be looking at how we can compute the value of definite integrals, or the area under a curve, for functions where we can use geometry to help us make that calculation. So, we know that the area under a curve, okay, and that means the area between the curve and the x-axis is equal to the limit as n approaches infinity, the sum I equals 1 to n of f of xi star delta x on the closed interval a, b. Okay, and the way that we define our xi star and our delta x is going to depend on a, b. So this right here we call a Riemann sum. Okay, so we have another way now of writing the area. This is called the integral notation. So this is a, b, f of x dx. Okay, and we would say this is a definite integral on the closed interval ab. So we would say this is the integral from a to b of f of x dx, and I'll write that here. So this is the integral from a to b of f of x dx. Okay, and that's just how you would say this little symbolic portion right here. Okay, so what we're going to do for this lesson is we're going to look at using this notation, but with functions that we actually can find the area of using a different method than Riemann sums. So let's take a look at an example. And so the examples we're looking at today are all functions that the area under a curve is going to have certain geometric properties. So let's try the integral from 2 to 4 of the function 3 dx. So let's draw a sketch of that. We have 2, 4, and 3. So y equals 3 is a function. It's a horizontal line. So if we draw in here at 2 and here at 4, the area we're trying to find here is the area of this shape, and this shape is in fact a rectangle. So the rectangle area of a rectangle is base times height, so we can use that area formula. So we would say the integral from 2 to 4 of 3 dx is equal to base of our rectangle, which is 2, times the height of our rectangle, which is 3, which is equal to 6. So we've managed to get an integral without really knowing how to compute an integral of a function, just by finding an area. Okay, so let's look at another example. Okay, the integral from -1 to 2 of x plus 3 dx. We do need to write the brackets because that's the function. We're thinking of dx as multiplying it. Okay, so let's draw a sketch of our function. So y equals x plus 3, we have a 1, and we have a 2, we have a 1, 2, 3, 4, 5. So our y-intercept is 2, and our slope is 1. And we're going to need, since we're going from -1, we're also going to need a -1. So this is -1, comma 2, 1, comma 3, 0, comma 3, 1, comma 4, and 2, comma 5. And so when we draw this line in, we can see that we have a trapezoid here. You may not have seen a trapezoid in a while, but this is the area that we are trying to find. Okay. So a trapezoid, we have two parallel bases. We can think of breaking it into a rectangle and a triangle, or we can use the area formula for a trapezoid directly. So this area equals base 1 plus base 2 over 2 times the height, where B1 and B2 are parallel lines. Okay, so our B1 is here. This is our B1. This is our B2. And our height is the perpendicular distance between them, so that's that length there. So my area is, this is a height of 2, this is 5, our base 1 is 2, base 2 is 5, so 2 plus 5 divided by 2 times our height of 1, 2, 3. So 7 divided by 2 is 3.5, and 3.5 times 3 is 10.5, or 10.5. Okay, so for example 3, if you've had a chance to look at some conic sections, that's great. Most of you haven't. So we're going to have to look at what the equation of a circle looks like. So we have x minus h squared plus y minus k squared equals r squared is the equation for a circle with center h comma k and radius r. Okay, so what that means is that we may be looking at functions, some functions that give a half circle. So we can, for example, 3, let's take a look at the integral from 0 to 3 of radical 9 minus x squared dx. So whenever you see a radical something minus x squared, your mind is going to pop and think, huh, circle. So how do we know what's happening with this circle so we can sketch it and use it to calculate area? Well, we know y is 9 minus x squared. So that means y squared is 9 minus x squared. And so we get x squared plus y squared equals 9. Okay? So this right here is a circle with center. Well, we're not subtracting an h or a k at all, so that means our center is 0, 0. And the radius is the square root of what our x squared, x minus something squared plus y minus something squared is equal to, so that is 3. Okay? So we do have to keep in mind, though, that our original thing is a positive square root. So this means y is going to be greater than or equal to 0. So when we're sketching our circle, we're only thinking about the top half of the circle. If it were y equals negative that, we would be thinking only about the bottom half of the circle. So our sketch is going to look like this. We have a circle with a radius of 3, but it's only the top half of the circle. So it's going to be like this. And if we're taking the integral from 0 to 3, so this is the radius, that's 3, we're only really looking at the area from 0 to 3. Okay, so this is the area that we're looking for. And so we are doing, this is a quarter circle. So this is going to be the area of a circle, which is pi r squared, divided by 4. And our radius is 3, so it's pi times 3 squared over 4, which is 9 pi over 4. Okay, and you do have to be a little careful about whether it's the positive or the top or the negative or the bottom. And so we've done trapezoids, we may hit a triangle, we may get a rectangle, and now we can do a circle. So those are the different kinds of equations we can solve just by using area formulas. We can also combine them if we know some properties of definite integrals. So these properties of definite integrals apply to all definite integrals. So once you start learning some more complex ways of computing definite integrals than just using geometric area, these are still going to apply. So let's have a look here. Properties of definite integrals. Okay, and there are a few, and then we'll look at an example of how we can use these to combine some stuff. So the integral from a to a of f of x dx equals 0. So if you're trying to take the area under a curve at just one point from only one point, it's 0. A straight line doesn't have any area. So the integral from a to b of f of x dx is equal to negative the integral from b to a of f of x dx. So what happens, what this is saying is that if you switch the order you're doing it, so instead of counting the area from say 2x equals 2 to x equals 4, you try to count it from x equals 4 to x equals 2, you're going to wind up with the negative of what you get, of what you would get if you did it the right way around. So if we try to, just like if we're counting area below the x-axis, we wind up with negative area. If you try to count area backwards, you are going to wind up with negative area. So you can switch the order, but it makes it negative. So 3, we have the integral from a to b of c of f of x dx. So if you have a function that's been multiplied by a constant, this is equal to c the integral from a to b of f of x dx. So multiplication by a constant can be taken outside the integral sign, and that can be really useful as we go forward. The integral from a to b, just like with derivatives and with limits, of f of x plus g of x dx equals the integral from a to b of f of x dx plus the integral from a to b of g of x dx. So if you're integrating a sum, you can integrate each piece of your sum separately. And the same goes for subtraction, because subtraction is just multiplication by a negative and a sum. So f of x, the integral from a to b of f of x minus g of x dx is equal to the integral from a to b of f of x minus the integral from a to b of g of x. Whoops, forgot my dx. So 6, the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So you can integrate partway and then keep integrating. You can integrate in pieces, and even cooler, c doesn't actually have to be in between a and b. So you can integrate to one far point and then integrate back, and that will still give you the same, and that's kind of a combination of some of the rules above. So c does not have to be between a and b. Doesn't have to be in the middle. And number 7. Okay. If f of x is positive or 0 for all x on its interval, then its integral is positive. And that makes sense, because if it's above the x-axis, that means that the area is going to be a positive area. And conversely, if f of x is less than or equal to 0 for all x on the interval ab, then the integral from a to b of f of x dx is going to be less than or equal to 0, negative. So if a function's all positive, your integral will be positive. If your function's all negative, your integral will be negative. Okay, so example number 4. This is the last one. So how do we use these rules if we have some kind of funky thing going on? Let's take the integral from 0 to 3 of 4 minus 2 radical 9 minus x squared dx. Okay. So now we can split this up using some of our properties of definite integrals. So this is the integral from 0 to 3 of 4 dx minus 2 times the integral from 0 to 3 of radical 9 minus x squared dx. Okay. We know the answer to this from example 3. We could draw a diagram, but we don't actually need to. So from 0 to 3, 4, remember that's just a rectangle with a height of 4 and a length, a base of 3. So this is equal to 3 times 4 minus 2 times 9 pi over 4, which equals 12 minus 9 halves.